There is a big difference. And a car factory on the other side of the wall really wants to have their castings. Otherwise, a few thousand people are waiting. So there's a totally different risk.
Yeah. Maybe also this risk assessment is also that this is where we see also a change in the methodology of working with a simulation, because the necessity to analyze your process, your nominal process, and also variations of your process. We all know that the casting process has variations. The initial casting temperature varies a little bit, the die temperature varies a little bit, the flow rate through the cooling varies a little bit, the die wears out a little bit. So there are a lot of variances in the process. And it became far more important now to analyze early, in an early stage, analyze also the variances of your process on the virtual side, to get the full picture. So again, until today, I could live with some iterations of your nominal process conditions. But nowadays, and especially looking at these gigacasting tools and processes, you have to, on the virtual side, you have to be sure that the process and all its variances are covered with your risk assessment.
Hello and welcome to the Gigacasting podcast. Today we are talking about something very, very interesting, meaning risk mitigation via using advanced softwares for simulation, casting simulation in short. And we are extremely happy to have Mr. Horst Brahman with us. Mr. Brahman has a long career in this. Many of you have probably met him at Eurogas or heard his speeches on various locations. And sooner or later, you do really want to dig into things. So that's why we're so happy to have you on board today, Horst. Welcome.
Yeah, thanks for having me here.
Yeah, pleasure is ours. Pleasure. We know you. Maybe someone out there doesn't know you. So could you please introduce yourself?
Yeah, of course. Yeah, my name is Horst Brahman. I'm working for Magma since 11 years now, or nearly 12 years. I worked for a couple of years in the foundry industry as an engineer. I studied foundry engineering. Unfortunately, it's a study that is dying. We're trying to keep that up, also with the podcast. Yeah, I'm in this business quite a while, for especially also in simulation, working for Magma. Maybe not known to everyone. So Magma is actually a company that develops and sells simulation software for the foundry industry. We are a mid-sized company with some subsidiaries all over the world, in the US, in North America, South America, in Turkey, in China, to be close to our customers. I will not name all the subsidiaries, but we're about 8 or 9 subsidiaries right now. The headquarters is in Aachen, in Germany, in the most western city of Germany. We are working in this business since in 3 years, it will be 40 years, in developing and providing simulation services and software to the foundry industry and all industries that use castings. And this is essentially our, let's say, motivation and our vision. We call ourselves to be committed to the casting industry, to be committed to casting.
You have been doing this for so long. You have done probably some mistakes that we're not aware of, but you have done a lot of successes. And there are some unique things around this with Magma. I mean, I'm a part of the case because we're running Magma day and night, actually, and we're pretty happy with it. But the aspects of your products, could you mention a few of those?
Let's say everybody knows maybe the way of simulation. Today it was an iterative process. So you have an idea, you try to simulate that idea and try to evaluate, is it a good or bad idea? Will it work in the real process? Now, since 8 years already, we changed this way of working a little bit, and this is kind of a USP that is still in the software, and that is putting all or most of your ideas into one simulation project, trying to, let's say, evaluate your different ideas, for example, different gating systems for die casting, or different positions of overflows, or different process parameters, putting all that into one simulation project and running a so-called DOE, design of experiments. So having a whole bunch of simulations in one project, fully automated, processed fully automatically, and then assessing the results within a statistical approach. This is maybe one USP, this so-called approach of design of experiments. It's connected to a certain methodology of working, of course, because you have to define your targets in the first place before you start the simulation. This is a very important aspect to really know where you want to go with a simulation. And then defining also, how do I measure my targets? What are the results that I will use to assess the different versions, the different ideas I wanted to try? Maybe the second USP that is really worldwide working, and we're trying to put a lot of effort into this, is our support. We, as I said, we're committed to casting. We have quite a high number of well-educated casting engineers, foundry engineers at Magma, and we try to be very close in support to our customers and help them every day as good as possible, as fast as possible, and as reliable as possible. Yeah, this is our daily motivation, I would say, that we're working for our customers. We try to generate a benefit for our customers because this is the essence of using simulation. Of course, it has to create a benefit at the foundry, at our customers. And what comes with this support is, of course, that you need well-trained people to operate our software. And this is maybe the third USP, that we have a so-called Magma Academy program that is also spread worldwide to all our subsidiaries, doing on-site training, doing local training in the territories very extensively to get the best usage as possible at local sites.
We used to say at Comtech, I don't know if you agree with me, but making a simulation is one thing, reading the result is another thing.
Yes, exactly. This is also part of our Academy program, so it's not only about the handling of the software. Of course, this is important, that there's this saying, shit in, shit out. If you put wrong parameters into a simulation, you will get wrong results. But anyway, you have to discover, are the results wrong or not? Even if you put good parameters into a simulation, you still have to identify the quality and the reliability of your results. And this is part of our Academy training. We have dedicated seminars and workshops to exactly teach and train and qualify not only the users of simulation, but the users of the results of simulation, which is far more in a foundry than just, let's say, the one that applies the simulation and puts in the parameters.
Absolutely. There's also that quite a big gap when you see that, for example, design departments, they are constantly running the simulations, adapting the tool design, but then it comes down to the first sampling round. And if you haven't read your simulation or don't put in the process know-how into the simulation in reading the results, you have a terrible time. And we all know how stressful samplings are, especially when there's a strict timeline behind it. And I think there's a big advantage that you can do a million trials that don't work until you get to the last few 10 millimeters plunge distance here and there to really try it on the machine.
Actually, at Magma, we have let's say, a certain mindset, because if you bring it down to the very point, then everything you do in applying simulation is a sort of waste until you read a result and create a measure out of this result. Actually, this is the point where you create value. So simulation is one point, but using the result to create a measure that actually makes you more competitive or generates more profit or reduces resources or works into the sustainability of your foundry, this is where the value is created. And this is where we try to communication with our customers to train people to create this value, exactly this point.
So the measure is just the aim for the simulation, to get your scrap rate down, to increase the overall OEE and things like that.
Yeah, that must be a great thing about sustainability. I mean, let us discuss that for a while. First of all, you have the waste, which is just waste, and that is bad for the environment. Everybody can understand that one. Then you have the long-term thing, supporting the EV development. So how do you see that? Because for me, it's a drastic change. It's a massive change. It's not only a gigacasting, it's new subsystems, carbon dioxide systems. We see new drivelines, number of parts going down from 2,000 to 400 something ish. But yet everything is new. Have you seen a dramatic increase in the use of your simulation softwares and the need of competence, or how is this affecting you?
Yes, it is a dramatic change, I agree, in the industry. In terms of simulation, it doesn't really matter if you use simulation for an EV casting or for a hybrid engine casting or for a combustion engine, that doesn't really matter. Of course, you need a certain knowledge to do so. But what really changed for us and puts also new challenges to Magma and to the users and the foundries is the development cycles of EV cars are, or I would say especially for EV cars, are much shorter or are getting shorter and shorter compared to, let's say, the conventional classical development process of, let's say, combustion cars. And this is a real challenge because this is also challenging the methodology and the duration of simulation, of course, to shorten the time from putting a question into the computer and getting the answer or a possible solution out of the computer. That is definitely it's not a new challenge, but it's got a new intensity.
Yeah, also when you consider that the requirements did change quite a lot, especially for the EV parts, you usually have way longer flow lengths. You have leakage requirement on structural parts you never had before. Everything is welded, riveted, and that's usually happening at the end of the filling. So you have to be quite sure that you get a good metal there.
Yes, of course. Yeah, but these are, let's say, the specifications of the castings of course, changed also going to EV cars and having these large structural castings. And there, you're absolutely right. There, we also had to, let's say, implement some new features and way of working into our software to enable our users to and the foundries to evaluate possible risk as early as possible. But still, the real challenge is having this workflow being with our product. We are a process simulation, a so-called process simulation. So MAGMASOFT is used to generate a tool design, to generate or modify a casting design adapted to the process, and then generate process parameters to be used for the real process. So setting up, designing, and the layout of the process. Now, this development process, virtual development process, generates a lot of information that is essential and very important for the design process of the casting. And this looping back of this information into the design process of the casting is still a challenge nowadays. It's a task that is 20 years old, but it's still a challenge to get this loop right. And there's a lot of potential lies in the organization of communication and the workflow and connecting MAGMASOFT as a process engineering tool to people and workflows. This is also our daily challenge to
So
work
it's
on
a
that.
human factor that is hindering this looping more. I mean, the technology is the technology, the software is doing its job, and then it gets stuck on someone's desk.
As always, it's a human.
Yeah.
I would say. No, yes, no, absolutely agree. And we try to overcome, or let's say, support this human factor a little bit by providing tools that ease in, for example, the communication. One tool is called Magma Interact. It's a small software package free of charge. You can just download it to provide MAGMASOFT results to anyone in the company or to your supplier to, let's say, enable a communication process, or to your clients and customers to enable a certain communication process. So this is one way of supporting this communication process. And the other way is, for example, a technical way to really export results of MAGMASOFT, for example, a temperature result or a temperature field out of a die casting process into other software tools that are used in the design process. So you could imagine that you have a porosity, you do a filling and solidification result with our software, then you get a certain picture of a risk of shrinkage porosity, for example, in a casting. Then you can export this result and import it or provide it. We call it a mapping process. Provide this result to an FE tool to increase the quality of the result of the FE tool. Let's say, for example, considering certain defects or certain material specifications within your FE simulation, for example, a crash simulation.
So interesting. So what you're pointing at is the aim of MAGMASOFT is not, well, casting on the TV, as I told me when I started in the industry in 1997. It is more closing the loop now to actually embrace the full cycle from design via the risk mitigation to SOP that actually generates good parts.
Yes.
It's a pretty big world.
Yes, and it is a tough task still, but we're working on this. Really, we're working on this since 30 years.
Yeah.
Since the beginning of Magma, this was one of the highest motivation we have to close this loop and provide the so-called front-loading process. Provide relevant information as early as possible into the design process of the casting, because the king's way of sustainability is adapting the cast part design to the process. That's the king's way. Everything else is creating waste.
Yeah. I absolutely agree with you. But I'm so happy that I can work with a lot of gigacasting projects. And I always have the feeling that this is about casting 50%, but also 50% about risk mitigation. And sometimes I feel that there are so many people in the room, but I don't see risk mitigation people. And I would like to see more like someone that actually is constantly working on the risk. And in doing that, actually working more with the simulation. I don't know what your comment is on this, but if I make it short, I see simulation software as a risk mitigation tool in the first room.
Yes, absolutely. This is definitely, I fully agree. Actually, simulation is part of a so-called FMEA. It's a failure method analysis tool. It supports this process. And that's also the way it should be used and should be placed into the company. We often see, or let's say in 90% of the cases, MAGMASOFT is used in the process layout and design department. And we would like, or we're constantly working on connecting our tool to the classical failure analysis tools that are used already in the company, because this is actually, it's part of this. It's made for this. Yeah.
But you also included a couple of new modules. You have one for comparing costs. You can have 2 or 3 or 4. I don't know, the many alternatives, and you can play around with the gating and the multi-metal and everything. You get a direct comparison. But you also did an introduction of the carbon dioxide calculator. Was this a forefront thinking, or was it a demand from the market?
I would say a little bit of both.
Okay.
There is a demand from the market. I think we all know that, and it's obvious by now. But this is also an idea we had already for a pretty long time to connect MAGMASOFT closer to a cost evaluation and also, let's say, in terms of sustainability, and that's actually the carbon dioxide calculation. This product is called Magma Economics, and actually it's just a tool that creates several new results that could be put into your assessment. Yeah. So what we try to do is, until today, casting simulation is used to assess the quality of your process and your casting. And now we try to, let's say, just add some new results, an economical result or a sustainability result, to be part of your assessment. So you not only analyze your part by, let's say, the level of porosity or potential porosity or the level of the potential risk of cold flow or misrun, but you also add into your assessment the difference, for example, a different gating layout would make on your costs, on the resources you have to invest in terms of material or for the remelting process. And also you can evaluate the impact on your carbon dioxide.
Yeah, I kind of like
balance.
them. It's actually the modules I have been using in my life.
Yeah, I think going back to your point, that's quite interesting, especially mentioning the sustainability, the output, the part quality, and also the connection with the other softwares. So when you talk about especially thermal management of your tool, that also goes then into how long does my tool last? And all of these things are basically impacting your carbon footprint of the part. Is my insert living for 10,000 shots or is it living 100,000 shots? There's the impact, then there's the scrap parts, because when you have a hotspot, you should have porosity there. So you can dig down even further and find these things with these connections. Or is that too easy a thought of mine?
No, absolutely not. Actually, let's say the assessment of the tool lifetime or certain wear phenomena in the tool like cavitation or die soldering and so on that have an impact on the lifetime of your tool. These results exist already since 10, 15 years in MAGMASOFT. But Stefan, also you mentioned this gigacasting topic. Of course, the high invests into tools, into these large giga tools, the high invest put a new or maybe a different pressure now on these results. They get more important because you have to evaluate your tool lifetime in order to be able to work on that, because this is essential for your whole process and for your investment. In the past, for let's say small die casting machines, 1,200 tons or 2,000 tons, it was still there, and of course this was a potential to be evaluated, but it was not that important. And these topics, they became far more important than in the past.
I mean, look, practical life, taking down 50 ton of tool or 2 ton. I'm not saying I'm throwing around with 2 tons when I go to the gym, but I definitely don't throw around 50 tons. I mean, it's a different ball game.
And actually, this is maybe one of the biggest impacts on simulation also, that this gigacasting topic is putting a whole new pressure or intensity on risk assessment. This definitely, this is far more important than for smaller castings. You could live with an iteration tool or sampling or 2 or 3 sampling processes because you have to do some minor changes in the tool. You cannot live with a second sampling or a third sampling in a gigacasting tool.
No, with the small parts, you can put 10 of them in a crate and store them for a few weeks. There's no problem. But if you have like a 2-day production for gigacastings, your parking lot is full. There is a big difference. And a car factory on the other side of the wall really wants to have their castings. Otherwise, a few thousand people are waiting. So there's a totally different risk.
Yeah. Maybe also this risk assessment is also that this is where we see also a change in the methodology of working with a simulation, because the necessity to analyze your process, your nominal process, and also variations of your process. We all know that the casting process has variations. The initial casting temperature varies a little bit, the die temperature varies a little bit, the flow rate through the cooling varies a little bit, the die wears out a little bit, so there are a lot of variances in the process. And it became far more important now to analyze in an early stage, analyze also the variances of your process on the virtual side, to get the full picture. So again, until today, I could live with some iterations of your nominal process conditions. But nowadays, and especially looking at these gigacasting tools and processes, you have to, on the virtual side, you have to be sure that the process and all its variances are covered with your risk assessment.
So one big point for these gigacastings is also that you have new alloys. Going from an ADC12 or ALSC10 MNMG to an ALSC7 variant of the alloy, the castability goes down a bit. How do you manage different alloys, new alloys, especially talking about, again, sustainability when you want to have scrap streams that no other ones can use? So you're definitely getting new barriers and new specifications. Do you have then new material models, or is that quite similar?
Maybe material models is the wrong term. The right term would be material data sets. So of course, this is something we have to consider in simulation, the specific heat capacity, describe the flowability of a certain alloy, or the risk of die wear of a certain alloy, high magnesium alloys, and so on. This has to be considered in our software in MAGMASOFT. We provide on demand, of course, and also for, let's say, well-established alloys, we have dedicated material data sets to be used. So this is to simulate the flow and the solidification process of a casting. If it comes to the prediction of residual stresses and distortion of a casting, then you need, again, a lot more data for simulation. And there we also provide data sets, very specific data sets to, for example, simulate the distortion during the ejection process of a gigacasting, or predicting the distortion during a heat treatment process, for example, after the casting process, where you need a certain creep model to also consider the gravity forces that could bend your casting in your rack design. These are more complex models we use there, but this should show a little bit that we not only take care of the casting process. Nowadays, it's also very important to take care and to virtually analyze the subsequent processes, such as quenching process, the heat treatment process, for example, a trimming process also, or a simplified consideration of the machining process of a casting, in order to create, let's say, the full picture of my production process.
Amazing. But if you are interested in building a car that has the right dimensions in the end when everything is assembled, then I guess you're pretty interested in the deviation of your casting and how to actually treat it. What I see is this constant development. We have some 120 contracts with big machines out there, 80-90% of them in China. There's some criticism that only 20-30% are used in production, but with my experience, when people start to get this going, it will be the de facto standard. There's no turning back. But the question I have is, what kind of development do you see in the gigacastings? Will we still have those rear floors and undercradles and battery boxes with just working on making them lighter and thinner, or will we see even fewer parts and bigger parts?
Yeah, we hopefully do not see fewer parts. This would be bad for simulation and bad for the foundry industry. but let's say in terms of simulation, one trend we see at the moment is this topic of distortion. This is really one essential result we have to deliver, where we have to deliver reliable information to the designers. And this is a challenge in terms of performance of the software, I really have to say, because we're talking about very large virtual models, a lot of so-called cast or simulation elements, millions of elements in a simulation model that have to be calculated. And this is also a challenge to Magma to increase the performance of the software. It's always in combination with the hardware that is used. That is a combination you cannot ignore. And there we see a challenge for us to reduce the calculation time to, let's say, industrial applicable times. It is hard to accept that you could do a simulation for, let's say, a small oil pump in the same time as for, let's say, a rear underbody. So there will be a difference even in the future. We have to get faster on this. And we are working constantly on this, using different techniques to improve the software on this point. A second challenge we see is definitely in this topic of analyzing the process in, let's say, multiple process conditions. This is what I said before, this, let's say, comprehensive assessment of process variations. This is also a very important topic for us. And of course, it's bound to the performance topic, because you have to perform multiple simulations to get this picture. And maybe a third topic that is also maybe not directly connected to gigacasting, but it's part of a mega trend right now, is coupling virtual simulations, so the virtual process assessment, with real process data. So using real process data to do a more precise setup of your simulation, or transferring virtually generated data, for example, the settings of a machine directly to the machine to perform your first sampling process, or do changes in the serial production. So connecting these two worlds, the virtual side and real process, directly with interfaces. And maybe in this regard, one last comment. If we talk about exchanging data, then one hot topic for us also is, what do you do with this data? And everybody knows about these AI tools to generate information out of data. And then it doesn't really matter if it's a real measured data or virtually generated data. So also with every simulation, you generate a whole bunch of data. And this is also a topic we're working on. How can we use this virtually generated data to create a benefit for our customers to, for example, help create an assistant that helps you setting up your first simulation, or comparing simulations, or assists you in analyzing the results?
But I'm just curious, do you get a lot of feedback from your customers? I mean, you always get the feedback if you made a mistake and something is not right. Maybe it never happens to Magma, but at Comtech it could happen once a year maybe. But how do you get feedback from the real casting? So do you need to make like an R&D project and some kind of agreement with the foundry that you also are allowed to study defects in the casting, so you can get it back and see, okay, with the simulation, I see this defect?
Yeah, this is a very difficult topic, actually, I have to say. We do have all over the world several cooperation partner customers we work with very closely. But in general, it is difficult to get results out of the real process. And that is due to, let's say, the confidentiality of a certain project and so on. We fully understand this. But of course, this data is very important for us to, let's say, learn a little bit and do improvements in the software. So we need this information. But what is even more important for us in this regard is helping our customers to establish this feedback process, because this feedback process, it's nice if we get this information, it's very nice, but it is a necessity to establish a process that generates continuous feedback between the shop floor and the simulation guys, because in the end, this has to be a continuous communication to optimize and customize and adapt your simulation to the real process. This is a very essential process. As I said, we have a strong support and very good application team, and this is part of their daily work to help customers to establish this feedback process, which is really, really very, very important.
But then going back to the gigacastings, one experience we have at Comtech is that many foundries are super skilled in what they're doing. They're teaching us. But actually, pretty many of the so-called gigacasting organizations, meaning car makers, are lesser or more ignorant about casting than a normal typical foundry. There could be a car maker that is traditionally based on sheet metal, for example, starting casting operation. And the number of people that has knowledge are very few. So the competence massive, I might say. So, I mean, isn't this a problem that you also see that, okay, we have a simulation, everybody takes a look 5 seconds, and yeah, it looks good. A foundry guy will probably dwell 2 hours with 2 cups of coffee on this to find, the defects and the problem areas for discussing with the tool maker. So, in short, isn't the competence level among car makers going gigacasting as sometimes a problem?
I would say in general, let's say from my personal experience, in general, I would say this is, let's say, like a little bit like an up and down or part of the mentality of a company. In my past, I realized times where OEMs or casting buyers, I would say, could also be tier 1 companies, continuously outsourced casting knowledge to suppliers. Nowadays, I would say it changed a little bit. I do know a couple of companies, OEMs, and also tier 1 suppliers that understood that it might be helpful to have a certain casting knowledge in-house. And I see a trend to, or at least that's my personal feeling, I see a trend that they try to bring that knowledge back into the company. And especially because in the end, the design of a casting is created, let's say, at an OEM or at a tier 1 company. And in order to create this castable design, you have to have a certain level of casting knowledge in-house, I would say.
Yeah, that's absolutely needed, because in the design phase, you can take out several euros in part costs, but when it comes to the purchasing, then it's just about cents. So yet in the beginning, you have the biggest impact. But coming to another point, especially when we talk about gigacasting, we had it in Kassel in several presentations that reocasting is also becoming more and more important. And how do you handle that?
Reocasting, or we call it semi-solid casting. For us, it's not only Rio, it's also Tixo and all the different variants that are applied in the world. But semi-solid casting, of course, is a topic for Magma since, I would say, 20 years already, more than 20 years. It started in the very early 90s at Magma. And we implemented this special material behavior of having, let's say, a temperature and shear dependent viscosity in a material. We implemented this model into the software in the early 90s. We even had a small own foundry and did trials on this. And the foundry was unfortunately sold at some point. But it's a long story with Magma. And it's a sort of an up and down. This technology has, from my personal point of view, a very big potential. And lots of applications. Of course, the application has to fit to the technology a little bit. That is for sure. But right now, we see again a certain trend that it could, let's say, finally become a significant industrial application. I would put it this way. And from a Magma point of view, we have a sister company called MAGMASOFT for plastic injection molding processes. We had this model because it's very close to plastic behavior. We had this model in SigmaSoft. Now we implemented this rheological behavior into MAGMASOFT back again last year. So we are ready for anyone who wants to dig into semi-solid casting. We are ready for it. We have a special model called Magma Semi-Solid. It's pretty easy, actually, where you can apply this special logical flow behavior also in the virtual simulation. It has to be combined with special material data sets, again, because you need also special material data sets to describe the properties of the material. I would say we have the most commonly used alloys for aluminum and also magnesium we cover right now.
I can reveal that it works just fine. Typical A356 casting. And the interesting thing for us is that we very often look at the simulated result to look for metal meetings. That is the key thing when it comes to simulation and casting and semi-solid, to put that name. And interesting thing is that if you see a metal meeting, like in a carbon dioxide compressor, for example, you can bet you find it in reality there. We broke 500 housings and could show that we had a metal meeting pretty much on the spot that the simulation told us. We did it to convince a customer. So that was a good study, but it was a lot of broken parts. So again, it works.
Yeah. Also, for everyone who is not so familiar with the flow behavior of thixotropic slurries, every position in the slurry has a different flowability because of the shear forces. So nailing it on point is really a big exclamation mark if you really stick to that. And that's what Staffan just proved.
Then you get a little bit sad because everything works fine. And then when you start in reality, someone is pouring 2 deciliters of oil in the shot chamber in every shot. And then it's casting is filled of oil. And you go from a Formula 1 race team down to, I don't know what sport even.
That's hard to consider in simulation also.
Yeah. But one thing that interests me a little bit is, I mean, you're living and breathing this, but we who come a little bit on the side of the softwares, we see both from this pod and our daily work that it shows sign of a huge digitalization of the casting industry. Would you agree, or is it just something we stumble around here?
No, of course, I agree. Yeah. It's on the, let's say, numerical software side, the market is growing, and of course also the applications are growing. But also on the, let's say, what I mentioned before, on the data assessment, data collection, data assessment, and application of AI tools, this is also part of this strong digitalization trend we see right now.
Yeah, because we see chatbots for alloys and alloy information. We see defects tools, machine learning on very local projects around, for example, the 6,200-ton machine that people are developing. And 5 years ago, we didn't see this. So it has been a massive increase of, how should I put it, software initiatives. But if they will survive, another thing. But also one thing that interests me very much, I don't know if you can reveal this, but some car makers are working with us use topology, meaning, some grain boundaries, some forces, and then they let the computer make the first design of the shock tower, whatever it is. Are you thinking about combining your software together with this in some kind of nice, juicy, iterative process? So I started in the afternoon, and the day after I have the perfect casting, producible and with the right strength for my design of my vehicle.
If it was that easy, we would do it every day.
We wouldn't have any jobs then.
Fortunately, it's not. No, yes, of course we are. Actually, we started this kind of coupling different tools already more than 10 years ago. It's still, you can count these applications on 1 or 2 hands at the moment. It's not a standard application right now to couple different simulation tools, and especially using topology optimization. I would say 8 to 10 years ago, we took the decision, we really digged into this, and we took the decision to not implement a topology optimization tool into MAGMASOFT. We took a different way of enabling our users to generate adaptive designs using parametric geometries. It has limitations, of course, because you are working with CAD data rather than taking mesh elements away to generate your final geometry. But on the other hand, it has also some benefits working with CAD data because let's say the loop process is easier, at least if you work in one software package. This was the basis of our decision in the past, but we have to rethink this, of course. This is, again, a topic to rethink and to maybe take a different decision. It's very interesting. It has a very high potential using topology optimization for certain aspects, for certain tasks, maybe not for every task. Also, the definition of the boundary condition of the constraints and the objectives is a tough task if you use topology optimization. It's not that easy, but it has its potential, and we will rethink this. But anyway, what I want to say is, if you want to dig into, let's say, autonomous generation of designs and geometries, then we have something available to work with.
You do?
And it's, yes, it is based on parametric geometries and database of predefined default geometries you can use and then vary automatically. And this is again where this new integrated approach of, we call it MAGMASOFT autonomous engineering, comes into place, because you let the computer do the job. You generate a design that has certain variables to move or to change its place or to change its square section or to change the layout and then define your objectives. What do you want to achieve? For example, reduce in sand casting, for example, or let's say also in die casting, the position or the size of your overflows could be easily generated autonomously by MAGMASOFT using these parametric geometries. So there's a way of working, but topology optimization is a hot topic, and we will dig into this again.
I think one of the first cars that actually have a greater amount of these castings is the Cybertruck. If to believe some influencers on YouTube, and they were tearing it apart. And when you looked at the castings, you can see that the lines, the stiffening ribs, that they were more like sea waves. And according to me, it's a cooler design below the sheet metal than what you see on the street on the car. So it was very, very interesting. So, okay, that was a sidetracking there. But what you're saying is this is probably the future.
Yeah, it is part of the future of the foundry industry, because more or less 90% of topology optimized designs are castings. You cannot forge them.
No. It should be producible.
So if we want to support the foundry industry, then let's dig into topology optimization.
But if we're talking about the future of the foundry industry, I mean, it's pretty black out there. Car production is going down, and the parts are becoming fewer, and we have seen some colleagues going out of business. You heard the news too, and pretty well-known brands, actually, not only the small guys. And if you would give an advice to someone running a foundry right now, what kind of advice would you give them to not only surviving, it's so boring, to thrive and maybe find something or a way to get some better margin and a happier life and a more interesting day at the foundry? What kind of advice would Magma in general and Horst Brahman in particular give?
Yeah, I'm speaking for Horst Brahman in first place. And my advice would be to put everything on the cart of avoid things. Because if you avoid something, then you do not even start to produce scrap, because you avoid it. We have a lot of customers, they're doing a great job, and they're doing a great job on reducing scrap, which is very important, of course, in terms of be profitable, in terms of sustainability, everything. But for me, it has always been let's say, the king's discipline to avoid things. And fortunately, virtual simulation, is one of the very few tools that really enables you to avoid things. So I would put a lot onto this card, trying to avoid.
Makes sense.
And the other thing is, which becomes, I think, more and more important, is we had, especially in Europe, and I'm living in Germany, especially speaking for Germany, we had a very strong basis of very well-educated, experienced foundry people. And many of these people now go into retirement. And they deserve it, of course. But this leaves a lack of knowledge. The second card I would put a lot of effort into is trying to somehow cover this lack of knowledge. And again, I think a lot of potential lies in these data tools nowadays, trying to collect data from your process and converting this data into knowledge by using AI tools. And the same is for simulation. Also, simulation is actually a tool to not only collect knowledge and make it available at any time for any person, but it's also a tool that day by day use generates knowledge. For example, if you analyze a certain variable, let's say you want to analyze on a virtual basis, how does my casting temperature influence the porosity in my casting? Or how does the intensification pressure of my third phase influence the porosity in my casting? You could do, let's say, a setup of simulations, and on a numerical basis, on a virtual basis, analyze how your casting behaves. And this is actually virtually generated knowledge, real applicable knowledge. So this is a topic I would put a lot of effort into, collecting or converting data into knowledge.
It feels like this conversation is so much about going between the virtual and the reality and making this border or this transition as smooth as possible. Because, I mean, at the same time, you say I can generate knowledge via the simulation instead of doing a lot of tryouts and costly things. And it goes back and forth, and it's becoming less black and white. It's interesting on a philosophical standpoint.
Yeah. Also, when you apply all the steps in between, having a good simulation that delivers a good casting comes down not only just to the software, also to the communication, just to wrap it up through the whole company. And I think that's a great learning from today.
So much has happened. You know, when I started in the business 1997, it was a guy standing with his thumb in an open tool explaining to me how the metal was flowing during 20 milliseconds. And I remember I was thinking, how can he know this? I mean, it was guessing. And if you look today, I mean, it's been a couple of years in 1997, but I mean, no one would dream of starting a project or even make an offer on an RFQ without a bunch of simulations. So I mean, it's come a long way, but I still feel that people don't really understand how to expand this outside just the simulation of the flow of the metal. To put in all the other things that you're talking about, Horst, here with the CO2, the financial side of it, and actually start to design your tool for it. Because when it comes to the tool, people become pretty cheap. And they say, maybe we don't need that sensor, maybe we don't need that cooling channel. And then they end up with a problem anyway. And if they would go back and run that simulation again, they will see this is a failure. And then they don't avoid these mistakes that you're referring to. So interesting.
I fully, absolutely agree. And this is also our, let's say, daily motivation, our daily task, and also, let's say, our vision for the future to really make this process of virtually analyzing your process and finding the optimal conditions, finding the risk potential, knowing about your process before you even start to machine the tool, to make this process as easy as possible and support this process. This is what I wanted to say with, say, generating assistants that help you in assessing the results, finding the right conclusions. In the end, it's a colorful picture, but you have to find the right conclusions.
Yeah, but it's a cornerstone of casting excellence.
Yes, having an assistant, and maybe an assistant that is based on your own knowledge, on the projects you did before, on the simulations you did before. He just learns and assists you in analyzing the next complex path you have to cast.
I think that's also the perfect ending for the podcast. From what else you can do over into what an actually good organization implementing simulations can bring you in the future. Thank you, Horst, for that impression of the simulation side of the casting world. And also thank you, Magma, for sponsoring this podcast. And then just can say, don't forget to subscribe, and we'll see us in the next podcast.
Thank you.
Thank you.
See you.
See you.
Goodbye.
Bye-bye.
Bye-bye.